Okay, in this video I have a couple more polynomial functions, though as you can see they're already factored for you. I went ahead and drew a little t-chart and the graph to begin with because there's a couple other things I want to point out in this video. So hopefully you watched the first one, and those two entailed polynomial functions in which we had to factor. Okay, this one's done for you, the factoring part. Alrighty. So let's begin. The first thing is end behavior. One common mistake is looking at this and like seeing, oh, well, it's just an x, or so it's 1, or even it's odd, right? Or even x to the third. Sometimes people make that mistake. But what you need to kind of think about is like, if you were to expand this entire thing, what would it look like? So without actually doing it, I would have some sort of x times x times x, right? X to the third, so x to the third, and then I have one more x. So all in all, it's going to be similar to an x to the fourth polynomial. So the end behavior in x to the fourth, and they're all positive, right? All those x's, if I were to actually distribute this out, I don't want to do this, but right, x minus 2 to the third means that, and x plus 3, so I'd have to maybe, I guess, foil these two, and then take our results and distribute all of that. But I can see I would have an x times an x times an x times an x and x to the fourth. So end behavior, I always start with kind of lightly sketching in, alright? X to the fourth would do that. It starts high, it decreases, it does some stuff in the middle, I don't really know, and then it ends high as well, right? It ends increasing. The great thing about this being factored for us is we don't have to do it for one, but also I could already see the zeros, right? We have, if I set x minus 2 to the third equal to 0, then I know that 2, 0, let's go ahead and write it here, 2, 0 is going to be an x-intercept. Now I see the multiplicity is third, so I don't quite know what's happening here, right? M, the multiplicity is 3, but I do know it's going to cross. So just keep that in mind. Let's look at the next one. We have negative 3, 0. So negative 3, 0. And actually, I think I want to move this a bit more. Okay. So negative 3, 0. Right, and that multiplicity is also 1. It's odd, right, because it's to the 1 power. I only have one solution of negative 3. And now kind of looking at, all right, this overall is a fourth. I know those two are zeros, and because the multiplicities are odd, it's going to have to cross, so it's coming from above, and it crosses through here, right? Then it does some stuff, and I know it has to cross through here since it ends high. So I know the general direction now, right? Okay, well, end behavior we're good. We found the zeros, and we kind of checked our multiplicity as well. Remember, if it's a fourth degree, we can have up to 4 zeros, but we have 3 repeating and 1, so the zeros is good. We'll check turns as we complete it. So the test points just means we should test numbers in these intervals. So something over here, something in between these zeros, and then something over here. Okay, and then we may need a few additional points. Well, 0 is definitely going to be, x equals 0 is definitely going to be one of my test points, because I need that. We'll go up a little just in case I choose 1 as well. I need the y-intercept regardless. So the great thing about factoring, again, that's done and we can find x-intercepts, but now the y-intercepts, it requires a little bit of work. Not a lot, kind of depends on the problem. But, right, if I put 0 in for x, so I could go ahead and erase all this stuff here. don't think I need it. If I put 0 in for x, I'd have 0 minus 2 to the third, 0 plus 3 to the 1, right? That's f of 0. That's the y-intercept. So negative 2 to the third is negative 8 multiplied by 3 is negative 24. So my y-intercept, we don't have to scale the axes the same, right? And the x, I was counting by ones. Here I can maybe count by tens, negative 20 right here, so negative 24. Again, it's a rough sketch, right? Something right there. Alrighty. So we have that value. Let's do negative 4. So now if I do negative 4, one thing I like to do, all right, while it's factored, this is, this isn't too difficult to do, but let me go ahead and let's just write f of x down here, and I want to point something out. Okay. In the last section, in the last video, we had to choose some that were decimals, and I was like, just use a calculator around it. But I did state whether it's positive or negative. What I want to point out here, and I should have did this in the last video, is like, let's say we did choose the value 1/2 for some reason, right? Maybe there was a 0 at 1, and I needed 1/2. Without getting exact, if your function is factored, what you can do is check, like, all right, if I plugged 1/2 in here, 1/2 minus 2 is a negative, right? And a negative to the third is still going to be negative. All right, now if I plug 1/2 in here, 1/2 plus 3 would be 3.5, which is positive. And if I have a negative multiplied by a positive, I know the overall result would be negative. So sometimes, like, without getting exact values, you can still verify that it is in fact negative. So whatever I get in 1/2, I know it's going to be a negative value. All right. Now, I chose negative 4. So going back to that one, what I was saying is we could actually do this, but negative 4 minus 2 is negative 6, right? Negative 6 to the third. And then multiplied by negative 4 plus 3, so it'd be a negative 1. Negative 6 to the third is negative 216, I believe, times the negative 1 is a positive 216. See, so if these numbers just get out of hand, check if it's positive or negative at least. That's a great thing to do. I could have quickly looked like, all right, negative 4 minus 2 is a negative. Negative to the third is negative. Negative 4 plus 3 is a negative, right? Negative times a negative is a positive. So now I know at negative 4, and it's way up there at 216, right? I'm coming down like this. Okay, 0, we got negative 24 in there. And here's where you may want just a few more values and use your calculator. Because I don't know, does this thing do this, right? Like a parabola? Or is there an extra something in here? I don't really know. And that's the point where, like, how accurate do we want to be? We'd probably just use technology to get that accurate. But a few more of these values, we could do one. That'd be negative 4, I believe. So 1 would be up here, right, somewhere right there. If we did 3, that would be only 6, so 3 is not terrible. Somewhere right here. If I did negative 1, that would be negative 3 to the third, negative 27 times 2, so negative 54. So we could see now, all right, this negative 1 is way down there, right? And Negative 2 would be negative 4 to the third, negative 64, even further down there. So this graph is shooting way down here, comes up, and then does something like that. Again, use geogebra.org to verify. We'll probably pull this one up really quick at the end. All right. Let's move on to the next one. So we're going to take kind of what we just did in that one, right, and go a little quicker, simplify this. So the end behavior. I would have an x to the squared. So overall, we have a negative x times by, we have a positive x squared, and then we have a positive x squared. So it's going to be similar to a negative x to the fifth. So negative x to the fifth would start high and end low. And then it has some stuff in between that I really don't know yet. Right? End behavior. The zeros. We have negative x equals 0, so x equals 0 will be 1. We have x equals 1, right here, 0, x equals 1, and x equals negative 4. So I'm going to try to leave some room in here. Okay. Our y-intercept, we might as well do that one really quick. If x were 0, I know the whole thing would be 0 because of this first guy here, right? If I have negative 0 times, I don't care what's in the next one or the next one, 0 multiplied by anything is 0. So the y-intercept is also 0, 0, negative 4, 0, and then 1, 0. All right, so it starts high. Oh, we could also check multiplicity, right? We have multiplicity 2 here, multiplicity 1 here, and multiplicity again 2 here. So at negative 4, this graph should be tangent and it should go back to positive. Okay, and even multiplicity, remember it does not cross x-axis, it bounces off. And then x equals 0 is a multiplicity 1, so I don't know, we're going to need some values in here, right? But it's got to come back down at some point, and it crosses because the multiplicity is odd, it's 1, and then it comes up to 1, and it bounces off because that multiplicity is 2, right? Multiplicity 2 here and here means it should be tangent. Multiplicity 1 here, it crosses. So very rough sketch. It agrees with the end behavior we had. Oh, and the last one we didn't check turns, but we had at the most 3, and definitely there would be no way of getting more than that. On this one, we'd have at the most 4 turns, and decreasing to increasing. Let's see, so here's 1 turn, right? Then it's got to come up and down at some point, so there's a second turn, and then down and up is 3, up and down is 4. Each time it changes from increasing to decreasing or vice versa, that's a turn. So on both of these, the turns looked all right. All right, we have the y-intercept, we have our x-intercepts, we just need some test points. So here's a great example where I could test 1/2. Right, so if I do g of 1/2, again, I know I kind of need the value to see where it goes, but at the least we could tell if it's positive or negative. I'd have negative 1/2 multiplied by 1/2 minus 1 squared multiplied by 1/2 plus 4 squared. See, I don't want to do all this in my head, right? So 1/2 minus 1 here is a negative, but then it's squared, so it turns a positive. This is a positive squared positive multiplied by a negative. Negative times a positive is in fact a negative, which is great because my prediction was that it's down here, right, in the negative value somewhere. So that looks good. Now, if I want an exact value, I have to take, right, all that and multiply it out. 1/2 squared would be 1/4 times the negative 1/2. I'm going to change this really quick to an improper. 4.5 would be 9/2 squared is 81/4. So now I have 82/4 minus 2/4, right? Here's 82/4 minus 1/2, which is 2/4. So we get 80/4. Times it by, oops, this is multiply, my bad. Geez, I'm doing LCDs where you're multiplying this. That, when I wrote positive, that threw me off. Okay, but that's just, that is a positive times a negative. All right, so we get 81 divided by 32, so, not quite -3. So my sketch, if this is -1, -2, -3, close enough, right? And again, we would definitely just use a calculator. All right, so I'm going to test out a point here, -1. We'll test -5, and we'll test 2. So I'm going to do this really shorthand. We'll do g of -5. I'd have a -5, so it's positive. And then negative, well, no matter what, the next one is squared, so it's going to be positive and positive, right? No matter what is in here, we square it. No matter what is in here, we square it. It will always be positive. So therefore, the entire problem of determining positive or negative relies on the first number. If that first number is negative, the entire thing is positive. Once we get to positive, the entire thing is negative. So now we would just need to find a few of those values for accuracy. And, again, I don't really want to multiply out those large numbers. So that's where we would pull up GeoGebra or some test points here. So we'll go ahead and graph this one really quick in GeoGebra. Okay, I'm going to delete this old stuff here. All right. So that graph was y equals a negative x multiplied by, so parentheses, x minus 1 squared. Okay, and then we move over to get out of the exponent, parenthesis, x plus 4, and then square that. Alrighty, hit enter. Let's zoom out here, and now you could see why I didn't want to see those numbers. If I tested somewhere in there, -2.16 would have been 73, right? But then how accurate do you want this? Now I can't even see some of this that was going on in there, right? Again, you could create the table of values. Oh, I don't like how they changed my parentheses here, but it didn't, overall it didn't affect the graph, right? I just didn't like the way it looked. Remember that from the last one, you could also do these special points here. You could do the table and get some of the intermediate values. Okay, it depends how accurate you want to be. Really what we're looking for is the general idea, the general shape of this thing. So as we saw in this one, right, this actually went way up there. And then it's very, very steep. And that's because as the power of x increases or decreases, it really pulls these values in opposite directions.